Good afternoon, ladies and gentlemen. My name is Jan Široky. I work in the Czech company Energocentrum Plus, and I'm the leader of the Energy Twin team. Today, I will talk about analysis of tagged energy data using machine learning. My presentation is about machine learning. However, you do not have to be afraid of equations or some confusing stuff. I will focus on practical issues. I will start with energy data preprocessing, then I will talk about energy data tagging conventions, and in the last part of the presentation I will show a live demonstration how tagged energy data could be analyzed by means of machine learning algorithms. Let's start with energy data preprocessing. The key question is what variable you should use. If you should use actual values like power or flow, or the accumulated ones like energy or amount of water. For the sake of simplicity, I will talk about kW versus kWh. And in the chart you can see an example of these data. The blue line is kW, while the red line is kWh. And you can see that more convenient for analysis is definitely the blue line, so the kW. But there is a major problem related to kW data, and this problem is related to missing data. If there is a gap in your measurement and you would like to calculate aggregation over this period where some data are missing, you will probably get wrong results, especially if you are calculating sum. In case of kWh, you also face some problems, but you could obtain useful results, at least more valuable results than when using kW. So what is the conclusion? Our suggestion is to use kWh and convert it to kW. If you have equidistantly sampled data without any outliers, this is a very straightforward algorithm that could be easily implemented. But in the real world, you will face different types of outliers and steps in the data. And in the next slides, I will show you some of these real-world examples of the things you can face when handling kWh data. We will start with a simple outlier. Here you have a measurement where one value dropped to value 0. It's obviously suspicious, and this could be easily removed. In the next example, there's also quite simple outlier. The only difference is that the outlier value is not this suspicious value 0, but some reasonable value, but anyway, it's still an outlier. The next example is also quite common, and it's related to meter reaching its maximum. So as you can see here, the meter reaches maximum value and then it starts counting from 0. So if you see such a suspicious steps, usually this is the reason behind it. Another quite common problem is related to exchange of meters, and in this case one meter was replaced by another that is starting from some arbitrary value, and you can face step such as this. And in this particular case, things are getting a bit more complicated. Measurement dropped suddenly down to some lower level values, continued there for 1 week, and then it suddenly returned to the previous level. And all the differences are reasonable except of these two big steps. So it's more difficult to develop an algorithm that will handle this properly. And if you think that you already solved all kWh related problems, you came to something like this. So what we see here, there is a problem with communication, and the meter kept sending constant data for the period over a few weeks. And after fixing the problem, it returned to the values that were meanwhile integrated in the internal memory of the meter. And one can guess that what we do have in the SCADA system is definitely far from the real energy consumption profile. And for example, linear interpolation instead of this big step would be more close to reality. However, it's not easy to implement an algorithm that will handle such a step without any unintended side effects. So to conclude this part of the presentation, I would like to stress the importance of energy data preprocessing. Any outlier, any step in the data will almost for sure cause some problems in the subsequent analysis of the data. So do not underestimate this part of the job. Let's now talk about energy data tagging conventions. Energy meta tagging is well described in Haystack documentation. Here I would like to discuss just two issues. First of all, there are ready-to-use subtypes like electric meter, flow meter or thermometer. And there are also predefined tags that you should use with your meter. And there are important tags like equipref or siteref or spaceref that will allow you to define references. And most importantly, tag submeter off. If you have some complicated topology of meters, basically anything else than just main meters, you should make use of this to capture this relation between different meters in your building. Energy meter tagging is quite simple and straightforward. However, it's also crucial for the energy data analysis. It's very useful to think about defining virtual sensors. You can define virtual sensors using relation tags like submeter off or these references, but also you could be creative and use your own tags. I will show you some examples in the next slide. Here are provided 3 examples. How can you define a virtual sensor using filters? So first example is quite simple and it queries all the meters that do have a reference to site, my site. In the next example, we query all the meters that are submeters of a particular meter, my meter. And in the third example, we combine our own tags, voltage, high or low, with the standard tags. And what it does is that it queries all the meters that are on the high voltage and site reference has tag GeoCity Chicago. So basically all the high voltage meters in Chicago from my portfolio. Okay, and after discussing energy data preprocessing and tagging, we can move to the main topic, that is energy data and machine learning. In these days, there are multiple machine learning packages available for energy data analysis. The first 2 tools in our list are freely available packages written in R. Both of them do contain advanced modeling algorithms for energy data modeling. Especially the second one, that is maintained by the company KW Engineering, provides multiple modeling approaches and algorithms. The next one is also freely available package that contains very similar algorithms, and this one is a part of Linux Foundation Energy project, and it's written in Python. The following 2 tools are a bit older, but anyway they can also provide you valuable results. eCam is an Excel-based tool, and Universal Translator is a desktop application. Both of them are providing also multiple models that are ready to use for your energy data analysis. And the last tool is Energy Twin. It's a SkySpark extension. It uses very similar energy model that's used by the first 3 tools listed above. And Energy Twin will be used in the live demonstration in the last part of the presentation, because this particular tool uses together energy tagging and machine learning. So I will be able to demonstrate the both things together. And before we jump to the live demonstration, I need to point out that due to non-disclosure agreements, I'm not allowed to show you real-world data of our customers. I will be using artificial data. However, all the examples and stories that I will show are based on the real-world experience with machine learning analysis of energy data. Let's start with the model description. The energy twin model consists of two parts: time-dependent load and weather-dependent load. Time-dependent load consists of different profiles for each weekday separately, and also the average occupied day and the average unoccupied day. Weather-dependent load captures the relation between the outside air temperature and the increase in the energy consumption. So, for example, if I pick up just occupied periods, I can see that in case of increased outside temperature, we can see increase in the energy consumption due to cooling. And the same applies to unoccupied periods, but there is much lower energy consumption needed for cooling. And also important is this small table, but here we can see the model properties, statistical properties, and the target values defined by measurement and verification guidelines. And we can see that, for example, in this particular case, all the target values are met. Here we can see the model prediction. The prediction is depicted as a blue line and the measurement is the red line. And these lines are quite close together, so there is a good fit of the model. In this table, we can see some summary over this period, that is February 2020, and also the overall difference is quite small. And yeah, we can say that there was a good fit of the model in this month. But as all of us do remember, February 2020 was the last month when the things were normal. So let's have a look at the next month. In the first 2 weeks, we can see similar pattern. Everything looks okay. But in the mid of the March, some preventive measures were introduced in the Czech Republic. And as a result, less employees were allowed to go into the office, and yeah, we can see major drop in the energy consumption when compared to the prediction. We can see similar pattern during the start of the next week, but suddenly something strange happened. And especially during the unoccupied period, we can see major increase in the energy consumption. We have been investigated this, and the reason is the non-stop ventilation by air handling units without any heat recovery. And yeah, this is definitely good for preventing the COVID-19 infection, but it consumes a lot of energy. So let's have a look at the next month. And we can see that the measurement is completely different than the predicted values. And we can see the similar pattern as in the last week of the previous month, that the energy consumption during the unoccupied periods, during night and during weekend, is higher, while during the occupied periods, during midday, there is lower consumption than predicted. And surprisingly, these two effects do cancel each other out. And if we look at the overall difference, there is just a small difference in the prediction and the measured amount of energy. And this is quite important point, because if you will use some technique like heating degrees days normalization and using monthly data, you could come to conclusion that from the energy point of view, nothing significant happened in this building during this period. But the opposite is true, and the only thing is that there were two major factors that do cancel each other out. But it's important to understand it and to be aware of effect of these two factors. A valuable insight can be gained while comparing measurement and prediction, as illustrated in the previous example. But you would not probably want to spend the whole day looking at the charts and trying to find out some anomalies. Instead, you would like to employ some automation into this. And this is what we can do here. Again, we have a prediction and measurement, and we do also have a threshold that's defined as a prediction plus 20 kW. And this is the 20 that's in this threshold. And we can see the gray area is the amount of the estimated available energy when we are above the threshold. And in the bottom, we can see all the time step when such a situation occurs. But one can argue that 20 kW is not the suitable value for all the buildings in the portfolio, and I do fully agree. And for such a purpose, we do have also a relative threshold definition, and in this case, threshold is defined as prediction plus 50%. So you do not need to specify it in by means of absolute values, kWs, but instead of you use just percentage relative to the predicted value. And again, gray area is the amount of estimated amount of the available energy, and occurrences are in the bottom. So now I can create some spark that's defined by this criteria. Once we defined our threshold, we can check the results. Here we can see all the occurrences of the situation when measurement was higher than prediction plus 50% for the whole month, March 2019, for the whole portfolio of our buildings. And you can see that there's a lot of things happening, and we need to somehow prioritize. So we can sort according to estimation of available energy. This is the gray area in the previous chart, and let's say that these guys are usual suspects and we know the story, but this one, building transformator, is suspicious because we do not know the reason, and there was no problem at all during the first half of the month, and then we can see that there is some persistent problem. So let's have a look. I will select the whole month, and what we can see is that measurement was really close to prediction, and it was definitely not above this threshold. But here something strange happened, and almost majority of the time we are above the threshold prediction plus 50%. When we observed this, we contacted the building owner, and he finally were able to find out that the problem was caused by the installation of electrical current transformers with wrong multiplication factors. So actually nothing changed, but just the measurement was wrong. He was able to fix this after a couple of months, and we can see this in our data clearly, because here is the pattern that was seen before, that measurement is above the prediction, and suddenly when the transformators were changed to the transformators with the multiplication factor that should be used, we can see that there are no occurrences at all afterwards. I would like to point out that this particular example is not about the transformers and wrong multiplication factor. The important message is the advantage of systematic approach to the building portfolio supervision using tagging and machine learning together. By combination of these things, you can be far more efficient and focus just on the situations that are worth of investigation, and thanks to that you are able to provide more valuable results. In the last part of this live presentation, I would like to show you an example how you can leverage your own tags in the energy data analysis. In this particular case, each building has a tag region. It's either north or south. And let's say that the goal was to estimate the effect of COVID-19 infection separately for the all the buildings are in the south region and all the buildings in north region. For this, we can create virtual meters, and virtual meters do employ this function that will make this calculation for us. So let's check the code of this function, and we can see that it's really simple, and the query here is using this region in the filter, and afterwards it's just reading the data, making some aggregation of all the meters that are in that particular region. And here we can see the results. So the blue line is the aggregated measurement from all the meters from the north region, while the red one is the aggregation from all the meters from the south region. So behind these two charts, two lines, are aggregation of all the meters, of dozens of meters that are in each region that are calculated, and these aggregations are calculated on fly. So a lot of things are happening underneath, but yeah, we can see immediately the results. So let's have a look at the month where these preventive action were introduced in the Czech Republic, and we can see that there is some drop in the measured values over the north region, but we cannot be sure what is related to COVID, what it's related to weather or any other external factors. So let's try to use machine learning for the evaluation, and we had already identified the model for the aggregated virtual sensor for both regions, and we can use the similar view as we used in the previous part of the presentation. And yeah, let's go to the month of the interest, and we can immediately see what was we can see the influence of the COVID-19 on the whole region aggregated. And yeah, let's go to the next month when things were in the steady state lockdown. And yeah, we can see that, for example, during the occupied periods, we see almost 10% reduction. Please keep in mind that these data are slightly artificial, so these are not the exact numbers, but yeah, the story is very similar. And using this, we were able to answer such a complicated questions within just a few clicks using machine learning tagging together. And this brings us to the conclusion. So first of all, do not underestimate the energy data preprocessing. If you skip this, you can be sure that some outlier or step in the data will corrupt your results, and you anyway will need to return to preprocessing and start over from the beginning. So do not skip this. Use tagging. Use standard tags as well as your own tags that are tailored to your application. It can help you a lot and improve your efficiency. And most importantly, think about how machine learning can help you in your applications. When using machine learning, you can provide better results with less effort, regardless of the portfolio size. In other words, you can let the machine learning do the dumb part of the job, and you can focus on the most severe anomalies that are found in the data, and you invest your precious time just to the issues that do matter. And at the end, you provide more valuable results to the end customer. We have been touching just some scenarios how machine learning can be used in energy data analysis. However, there are others. And just briefly mention three of them. One of them is measurement and verification projects, when machine learning can be used for baseline modeling. The next one is peak demand prediction. It could be used, for example, for peak demand shaving. And the last one is identification of energy savings in your building portfolio. In other words, finding the black sheep in your building portfolio where there is the highest potential for energy savings. I hope that very soon machine learning will not be just a buzzword, but instead tools based on machine learning will be part of everyday job of energy experts and improve their efficiency. Thank you very much for your attention.